All right, so welcome to lecture 4. In this lecture, we're continuing our study of the single neuron model with respect to supervised learning. In the previous lecture, we learned about the single neuron model and how we can apply an update rule to the weights and bias of that model in the context of binary classification, which in that case, we used this sign function, like sign like -1 or +1 function as our activation function. And when we did that, it was called the perceptron. And the important thing that I wanted to emphasize from last lecture, that we were, regardless of the function that we chose as our activation function and what we were doing, what we really were, like the heart of what we were doing was updating the weights and bias of our model. Now, in this lecture, we're going to learn how to do this in a very efficient way. And we can do this whenever the cost function of our model is differentiable. Unlike the perceptron model, the sign function is non-differentiable. We couldn't really take any derivatives or anything. But in this lecture, we're going to learn where if we do have a differentiable cost function or any differentiable function, we can approximate minimum of that function or global minimum of that function with an algorithm called gradient descent. Okay. Now, in order to understand gradient descent, I'm going to first start with a function of a single variable. Now, when I was a grad student in the computational and applied math department at Rice, I had to take a course where we learned about gradient descent, and it was surprisingly confusing to me then. It's surprisingly because I look back and like, why was I confused? And I think the reason why I was confused about it was that I never saw an example of it on a function with a single variable, where the gradient is equivalent to the derivative. So in the first half of this lecture, we're going to focus on understanding gradient descent, and the majority of that will be from the point of view of a function of a single variable. So in front of me right now, I have a Jupyter notebook available on my GitHub account. And we're going to start by running this code that I have in front of me. In this code, we're defining a function of a single variable. It's a parabola, as you can see here. And the variable is w, which is kind of hinting at the variable being a weight, right? So if we're trying to optimize a function of weights, we should pretend that we're in that case. So here I have a single variable function, variable is w. W minus 2 all squared plus 1. So this is the parabola shifted over by 2 and then raised up by 1. And we're going to plot this to get a look at it. And then also import the main libraries that we always will, with the exception that we haven't imported pandas this time. But matplotlib, numpy, and seaborn. And I always use seaborn just because I like the seaborn theme. It's just, I like the gray background. So let's go ahead and run this code. Now, if you've been watching all my videos on like the crash course on Python, you should understand this code. I'm making a domain, and then I'm setting a figure size. I'm plotting domain, and then the function applied to that domain, giving it a label, setting my X label, my Y label with specific font sizes. And then I'm plotting my legend with a specific font size, but I'm giving it a location to stay out of the way. And you'll see why I'm doing that later. So to give the legend a location, just type in the keyword loc equals, and then the location in a string. All right, so let's see what this looks like. Wow, that's taking a long time to run. There it goes. Okay, so here's our function. Notice the location of the legend. It's up here. We have a title. The axes are labeled. And we have our parabola that's been shifted over by 2 and then raised up by 1. Nice looking little function. Okay. And what's our goal? Well, our goal is to minimize this function, to find the minimum of it. Now, obviously, this function has a global minimum at w equals to 2. Right? That's the vertex of this parabola. But we're going to suppose that we didn't already know the answer and then try to find it. Now, in general, this is a good technique when learning something new, learning a new type of algorithm. Give yourself an example where you know the solution and then work through the description of the algorithm and see if you can find that known solution. And that's what we're going to do. All right. So we're going to suppose that we don't know the minimum of this function where that occurs. And in that case, we wish to solve this problem. This is a single variable optimization problem. Minimize f of w, where w is just some real number. This class of problems falls into the realm of what's called unconstrained optimization. And for those of you that are more mathematically inclined, I highly encourage you to check out the readily available textbook of Nosidel and Wright on optimization. So this textbook, which there's a link in the Jupyter notebook that I've made, is kind of, I would call it a gold standard, honestly. It's the go-to optimization textbook for learning these techniques at the graduate level. And Nosidel and Wright give a extensive description of techniques for minimizing functions, like without any constraints, but then also with constraints. So the majority of the book is on unconstrained optimization. So there's no constraints on what the input variable should be or input vector should be for multivariate functions. And these methods all are about that minimization problem, min f of w, right? Where w in this textbook is treated as a vector, but we're starting off by treating w as a scalar, or it's a single variable, right? And it's an excellent textbook, and I encourage all of you to at least go through and look at maybe the introduction chapter, just to get a sense of what the like framework of optimizing a problem, optimizing a function with no constraints is. Okay, it's a great textbook. I own it, and I really like it. So I should probably mention though that the treatment of this type of problem, this unconstrained optimization problem given by Nosidel and Wright, is extensive and goes much further than what is maybe not currently implemented in machine learning, but what is typically implemented in machine learning when optimizing cost functions. However, not all of the techniques, but many of the techniques in the early chapters of that textbook focus on using the gradient, or in our case, the derivative, in order to search for plausible minimums of functions. So that's kind of the framework of this first half of our lecture. We need to somehow use the gradient or the derivative to help us search for a local minimum. Now I have to emphasize local minimums. In the general case, there's no hope for finding a global minimum of a function, but we can find local minimums. And we're kind of lucky with the example that I picked that this quadratic function is what's called convex, which means it has any local minimum will also be a global minimum. Okay, but that's not what it means, but it implies that. Convex functions basically are functions where if you pick any 2 points on the plot of the graph and you draw a line between them, it's contained above the plot. Okay, so I'll make more note of that later. So how are we going to do this? How are we going to use the gradient to help us out? Well, let's go ahead and get started by making a guess at where the minimum of our function occurs. And I decided to guess at 5. So I'm assuming that, I'm not assuming the minimum occurs at 5, I'm just guessing that maybe the minimum occurs at 5, right? When w is equal to 5. So shown here in magenta is my initial guess paired with the function's value at that guess. And as you can see, it's kind of far away from where we need to be, okay? So how can we adjust our initial guess to get closer to where we need to be, which is in the range of 1, 2, and 3, somewhere in that area, right? So the general idea behind this gradient descent method is to use that gradient, which means that this method is what's called a first order method. If we're allowed the first derivative of the function at any of the points in question, then it's a first order method. If we're allowed the second derivative, then it's a second order method. So that would be something like Newton's method for optimization. Okay, but we're just using the first derivative. We're going to exclude second order methods from our entire semester pretty much. So with our initial guess of 5, we're able to calculate the derivative at that value. The derivative at that value gives us the slope of the tangent line to that point, right? And with our simple quadratic function, we can easily calculate the derivative as just 2 times w minus 2. And this is like, I was trying to think of a good way to describe why this would work. And the best way I could think of is the fact that I currently have, I'm currently recovering from a broken fibula, the small bone in my leg, which I had surgery about 6 weeks ago on. And I started walking around recently. And whenever I encounter like a incline, I'm reminded that, oh, that's not fun. My leg is still very tender, right? So I made a little diagram here showing me on some slope, right? So in this instance here, I'm standing here and I'm receiving pain and it's not fun. And I'm reminded that like my loss function or my cost function is the surface I'm on. I'm penalized for being on a surface that's steeper, and it's much more comfortable when I can just stand on a flat surface. So how do I know that it's hurting, or why am I getting information that it's hurting while I'm standing on this surface, or well, suppose there's some function that's defining the surface that I'm standing on. Well, it's the steepness of the incline, and not just the steepness of the incline, but if I'm a two-dimensional being like I am in this diagram, this figure, it's also like what the sine of the steepness, the tangent line is basically, right? So if I'm standing over here and it's steep and the tangent line is positive, then I want to move to the left. If I was standing on this side and the tangent line had a steep slope, but the sine of it was negative, I would want to move to the right. So at any given point on this surface or this function, the pain that I'm receiving is kind of relative to where I'm at, and that information, which is given by the slope of the thing and the sine of it, and that's precisely the derivative at the point I'm standing at, it's going to tell me which direction I need to move to find a nice local minimum where the pain in my leg is not going to be so bad. Right? So how can we visualize this tangent line with this plot that we made up here? Well, I wrote some custom code here for us to have a way of visualizing these things. Now, this isn't necessary to implement the gradient descent method by any means. I only wrote this code for instructional purposes. But I think that it's also useful for you guys to see and know how it works, because in some instances, you'll be making presentations for like a master's defense or PhD defense, or you'll be making presentations for whatever job you end up working at. And you need to have this type of mindset when making those presentations. You need the images to be indicative of what you're thinking. So let's go ahead and walk through this code. So first off, I define the derivative of my function f at a given point, w, and it's just 2 times w minus 2. I set my initial weight, and then here is my special function that I wrote to draw the tangent line to a curve at a given point whenever I want to. So this function takes as input a scalar wi, a function, its derivative, and then some keyword arguments. And the keyword arguments are specific to, in the case of I equals 0, printing. The color magenta is my favorite scatter color. And show equals true is just a way of saying it by default that it's going to show the tangent line, and then sometimes I might not want to show it. So inside this code block contained with the definition of tangent line function, I write another function. So I don't think any of you have seen this yet. You can define functions within the scope of another function, and that's exactly what I'm doing. This function takes as input a w and then returns derivative of wi, which was passed into the super function. So because this is in the scope of the definition, it has access to whatever I pass in there, as well as the derivative, which is there. And then w is the only variable of this function. Everything else is within the scope of this definition of this function tangent line. And this is precisely the equation of a line with slope derivative wi, passing through the point wi and y, a value or function at wi. So that's all this is. This is just calculating. It's the equation of a line passing through slope and point. Hopefully you understand that. So I define this function, and then next up, I create a range of values to plot over, which are with respect to the wi value. So I subtract off 1, add 1, and I make 10 points in that lens space. So this is just a range of values to plot the tangent line over, where the tangent line is going to be at the point wi comma function at wi. All right, so if show is equal to true, that's by default, this is going to occur. I'm going to plot my w range, and then I'm going to call my line function on that w range. Again, that's just equation of a line with that slope passing through that point. Make it a nice little line width, color it red, and then give it the label tangent line. So that's if show is equal to true. And then after that, I scatter the point in question, wi comma function evaluated wi. I set the color equal to the color that was passed into the function. So by default, it's magenta. And then I give it the label wi. In fact, that should be different. The point label should be a pair. So wi comma f of wi, like that. All right, so that should be the point label. And then fix that. And then, so that's everything. This function doesn't return anything. It just plots. It plots a tangent line if show is equal to true, and then it always scatters the point in question. Right? And I made that so that I can use it over and over again as we're iterating through this process of updating our w's and observing the tangent lines to the function at those different w's. And then all the rest you should know. Make my fig size, I plot my function, I call my tangent line function to do the stuff that I just talked about, and then give my labels. So let's go ahead and copy all this code here, and then run it, and you'll see the nice looking tangent line. All right, so there's my tangent line. Nice picture, it's descriptive, and it's useful in describing the problem, which all of you should try to do when you're writing your project notebooks. You want things to be as descriptive as possible for people that don't have the chance to talk to you about it. Okay, so next let's talk about direction of descent and what's called the learning rate. So observe in this figure that the tangent line implies the direction of descent, right? Currently, at this point, the tangent line, the slope of the tangent line is positive and it's pretty steep. Since it's positive, we know that if we move to the right, we're going uphill, we're going up the function. But we want to find the minimum. So since the tangent line is positive, we want to move left. We want to subtract off of the value we're on instead of adding on it. So that's precisely what we need to do. We need to move in the direction opposite of the sign of the derivative of the function at our previous guess. Okay. But just because we know to move to the left in this case, how far do we need to move, right? If we move like a tiny little bit, we're not really making much ground. If we move maybe 100 to the left, we're going to be way off target. We need a way of determining how far we're going to move. And this value that's going to scale the value of the derivative at the previous point is called the learning rate. Nocedal and Wright called this hyperparameter the step length. So in unconstrained optimization, it would be step length. In machine learning, you would call it the learning rate, but they're the same thing. Both typically, in both cases, typically denoted by the Greek letter alpha. Now, what we're going to do is we're going to multiply the step length times the derivative of the function at the previous value, and then subtract this quantity from our previous value. This is called gradient descent. Even though we're using the derivative, I'm still going to call it the gradient descent. So this is the gradient descent update rule for a function of one variable. So we have a previous value. We're going to subtract off a learning rate times the derivative at the previous value, and this will become our new guess. Okay. So notice that not only are we, if we subtract off the derivative at the previous value, so just think about the signs. If the sign of the derivative is positive and we subtract off, like in this case, we're moving this way. If the sign of the derivative is negative, which would be like over here, then we subtract a negative, we add to our previous value, we move to the right. And so we're moving in the right direction. And the term alpha is kind of scaling how large this value can be. Okay. Now, the choice of the learning rate in machine learning is typically found by experimentation or like tables that you might come across, but I typically find it by experimenting with it. However, more sophisticated techniques are available, such as line search and trust region methods. And again, these are available in that amazing textbook of Nocedal and Wright. For our purposes, we're just going to choose a learning rate of 0.8. So learning rates are typically between 0 and 1. I should have said that earlier. And I'm going to choose one of 0.8. So in the following code, I have my initial guess. I set my learning rate, and then I apply the gradient descent rule. So W1 is equal to W0 minus learning rate times derivative at W0. I print out my sequence of choices of W, and then I plot my function, and I call my tangent line function twice on both choices of W. But notice I provide the keyword false here for the first one, which means that I'm not going to show the tangent line at the point W0, f of W0. And then here, tangent line, I do show it, the tangent line for W1, f of W1. I set I equals to 1 for labeling purposes because I want to label W with the subscript 1, and then I color it green. All right, so let's just see what happens when we run this code. So I copy that there, paste it, and run. All right, so notice what happened. We were at W 0, so W is 5.0, and then we applied the update rule, and now our new W is 0.19. So we moved all the way over here. So we moved in the correct direction. We kind of overshot the minimum, but at least we're closer now, right? So our new guess is a better choice of both extrema and minimum value for a function than our initial guess would have been. More specifically, we have moved down the function. And that's the whole goal. We move down the function. So now let's move again and see what happens. Note that the derivative at our new point is now negative. So when we subtract off learning rate times the derivative, we're really adding to our previous value. So we're right here and we're going to add now. So we're moving to the right, which is the correct direction based off of the figure in front of us. So all of this code is basically the same. Let's run it. All right, so we started at W not equal to 5, W1 was 0.19, and then we moved to 3.0 something, right? So we're kind of jumping around, and notice we're starting to head towards this bottom, right? So let's run it one more time, apply this gradient descent update rule, and see if we get closer. Again, we're getting closer, right? But we're like starting to like hone in on where the true minimum is, which we're pretending we don't know, but we actually do know that it's going to occur at W equals to 2. So we're getting closer, right? So let's go ahead and just iterate this function iterate this process with a function. This is really easy to do. We're going to write a function called derivative descent. It takes as input the derivative of the function in question, a learning rate, an initial guess, and then the maximum times that we want to iterate through this process. And inside this function, I make a list that's going to store all of my guesses because I'm kind of curious to look at them maybe a little bit later. And then I have a counter to make sure that I don't overshoot my max iterations. And then while the absolute value of the derivative, the most recent choice of the derivative, recall, -1 is the index of the last entry of W. So while the absolute value of the derivative evaluated at my most previous choice of W is greater than some small value, recall, if the derivative is 0, we're at a extrema, right? We're possibly at a local minimum. So that's all this is saying. Like if I'm close enough to being at a local minimum, stop, right? So I make a new W inside the while loop, which is my previous W. Again, the most recent, the last entry of my W, which is the most recent W. Subtract off the learning rate times the derivative at that entry. And then I pin that into my W list. Increment my counter variable. And then outside of that, I convert it to a NumPy array, return it. And then that's my function definition for derivative descent. I set a variable W equal to this function evaluated on the derivative that I defined above. I print out my possible W's. I do a little bit of rounding here using NumPy. And then I plot the function, scatter the W's that I encountered. And then I use my tangent line function on the very last W that we found. So whenever that while loop exited, which we called there. So let's see what happens here. So I just copy that and run it. All right, so here is our initial guess at W equals to 5. We jumped around, and then notice in blue is our very last guess. So after 19 iterations, we broke out of the while loop, which means that the tangent line to that point is sufficiently close to 0 in absolute value, which means we're at some possible local minimum. Now, again, we found this local minimum because we had the correct choice of step length or learning rate, and also that this is a convex function, right? If this function was kind of curvy all over the place, we could only like be sure that we would find a local minimum. It just happens to be here we found a global minimum because it's convex. Again, I have to emphasize that a lot. So this would be equivalent to me finding this local minimum where I can stand without any incline, which means the derivative at that point is 0. I don't have any pressure on my legs, and I can finally relax and have a beer at Valhalla.
Excuse me, I have 2 questions.
Yeah.
So they're both about this value alpha. So I guess I was wondering like what the intuition is that alpha is less than 1, because I'm thinking of like a geometric sequence, for example, and like that will go to 0 if you pick something that's less than 1 in absolute value. Is there any like analog to that in this case, or intuition?
Well, I'm glad you brought that up. I wasn't thinking of geometric sequences or series, but we were like I was about to talk about looking at different choices of alpha.
Okay.
All right, so let's see what happens when we try different learning rates. So 0.1, 0.5, 0.8, 0.9, and apply the derivative descent algorithm to our function with the same number of epochs and just see what happens. Or not epochs, the same number of iterations. So let's copy this code. Notice that I'm not using plt.plot, I'm using subplots. And the reason why I'm doing that is I'd like to make a grid of figures, and this grid will be 2 by 2. The full grid is 10 by 10 in size, and this is called fig comma axis, with is going to be equal to this. So there's going to be 4 axes, and those axes are what I'm going to loop over in this for loop. So for x comma alpha, so it's pairing up the x and alpha. So each axis is paired with an alpha because I'm calling from this zip function. So for each of those pairs, I'm going to apply derivative descent with that choice of alpha. And then I'm going to plot over the domain that I picked earlier, scatter the W's, and then I'm going to set each title to know how, like, what the choice of alpha was and how many iterations we have, and give it a given font size. So let's focus in on, I guess, the top 2 here. So when alpha was 0.1, it took 40 iterations to get down to a sufficiently small gradient value or derivative value. So it took a long time, right, relative to what we did earlier. And that's because the step size was, or I'll call it a step size, was so small, right? So it's taking itty bitty steps, and it took a while to get there, which is completely different than a step size or learning rate of 0.5, where it only took 2 iterations, basically initializing the W and then applying the gradient descent method one time, and we landed on the perfect spot. So huge difference there. Like 0.5 seems kind of optimal based off of our starting location, right? Now, at alpha equals to 0.8, we already kind of saw that, right? And it took 19 iterations. And then at alpha equals to 0.9, it took 40 iterations again, right? So this is a case of large step length. So jump from 5, way over here, way over here, way over here. These large step sizes are making it a little, it's making it take a long time. So just to illustrate a point, let me change 0.9 to be 1.0 and run this again. When the step size was 1.0, look at the number of iterations. We never did anything. We jumped from 5 to, like, it looks like -1, back to 5, 1, so forth. Every single time we jumped to the same spot. Look at all the points being clustered up there. This is a case where gradient descent will not converge even when we have a nice convex function like this. And it's because the choice of alpha was too large, right? And this is where you have to be very cautious with the choice of alpha that you pick. And it also depends on where you start, but even then, sometimes you'll run machine learning algorithms with a alpha or learning rate of like something even like 0.05. And you'll see that your solution is not, it's all like NaN values. It doesn't make any sense. And you're like, why is my gradient descent not working? It's because your alpha was way too big. And a learning rate of 0.05 in some cases is way too big, especially depending on the size of the variables in question, right? Like lots of weird things can happen when, like, you have like one input to your cost function, like feature vector input, like entry is in the range 0 to 1, and the other is in the range like 1,000 to 5,000. When the scaling is off like that, you have to scale the data first, honestly, but still you have to be very careful with these large step sizes because of this behavior of jumping from one spot to another and then back to the same spot. And that happens whenever alpha is 1 or higher, pretty much is the only time that, well, in this case, that'll happen. But for some models, even what you would think would be a small learning rate is still too large for the data at hand. And the way that you'll measure that is by observing how the cost function is behaving over each iteration or over each epoch. Okay. So that was looking at gradient descent of a function with one variable. Let's now move to the real case, applying gradient descent to a function of multiple variables. Okay, so in this case, we want to minimize f of w, where w is some n-dimensional column vector. Okay, now, if you understand the case with single variables from functions, it's basically the same thing. For example, you can imagine like a function of two variables, like this function w0 squared plus w1 squared plus 1. You can imagine like this process of finding minimums as doing it in one dimension and then also the other dimension. So in order to update both dimensions, we, instead of using the partial derivatives in this case, well, not single derivatives, we use the gradient, which is a column vector of the partial derivatives. So with true gradient descent, our weight vector, which in this case has two entries, it becomes our previous weight vector minus our learning rate times the gradient at our previous w, or previous weight vector. Now, as before, this function of several variables is a example case where we know the solution. The minimum of this function here occurs at the weight vector 0, 0, right? So before we show how the gradient descent is going to work on this case, let's go ahead and run this code here to kind of get a sense of how to plot three-dimensional functions in Python. So the way that this works, well, first off, I import a module from NPL toolkits. It's mplot3d. It's an easy way for me to plot three-dimensional surfaces. I define my multivariable function, and then I make a x and y lens space of the same size. Once you have that, what you can do is make what's called a mesh grid calling NumPy. So the NumPy mesh grid method takes in those two lens spaces and creates a mesh for visualizations. I guess we'll just have to look at it. And then for our z values that we're going to plot, we apply f to that mesh. All right, so then I make a figure and then set my axes here. I don't need to repeat that line there. And then I call the contour 3D method to sort of plot that for me. In fact, I don't even think I'm using my MP plot 3D thing right now. I'm not. Yeah, I don't even need that. I was doing something else earlier. Let's just run this and make sure it works. All right, so there's my contour plot in 3D generated by taking a mesh of x and y and then applying the function to that mesh grid. And it looks kind of nice and it's a good visualization, but it's kind of hard to kind of view the minimum down there. So we can just repeat the same code, except for now we call the view init method here and provide the location of where we're viewing from. We've run that. Notice now that we're looking into the bowl, like this convex function. Again, this is a convex function. We're looking in there, right? So it's a different way of viewing these three-dimensional plots. Okay, so now that we know how to view them, we just need to apply the true gradient descent method. W is equal to W minus alpha times the gradient at W. In order to do this, we have to define our gradient, which is precisely this. Easy for me to calculate, just 2 times W0 times, or comma, 2 times W1. Convert that to a NumPy array. And then I write a new function called gradient descent that takes in the derivative, a W vector is our starting choice. I don't even know why that's there. There's no need for that W0. So this is like our initial vector choice. We have a learning rate, maximum number of iterations, a counter, and then I'm going to keep track of my weight vectors with this W hist list. So I put in my initial one there. So then while the counter is less than max iterations, apply gradient descent. W equals W minus learning rate times the derivative at W. Increment my counter, add to my history list, and then return my history list. The very last entry of my history list will be the final choice of the W column vector. So then I assign the variable W equals to the gradient descent method, or function, I mean. Right, and as my starting vector, I suppose the solution is at 5, -5. Make my mesh grid again. I plot my function, and then for each, this is ugly code. I should have done this different, but basically for each I in range, the length of this W, which again, that's the historical records of updating my weights. I scatter the 0 entry, the 1 entry, and then the Z value, which is F applied to the 0, 1 entry, and I color it blue. Set my labels, change my view to be 60 by 35. So if we run all this code now, we will see something. And there it goes. Look at that. We started over here, and then we apply gradient descent, and we're going downhill to the bottom of the bowl. And again, this works amazing when you have an appropriate step length or learning rate, I mean, and your function is convex. Your function is a bowl-like thing, right? Which I would like to highlight that in my previous lecture on the single neuron model and defining a cost function, the cost function that I defined had a square term over the differences in y hat and y. The cost functions that I were defining were quadratic functions. They're convex, so we can hope to optimize them well. Okay, so I'm going to go ahead and stop this recording. This is the first half of our lecture. In the next half, we're going to learn how to apply this gradient descent method to optimize the cost function of a single neuron model.